Okay, so we're going to be going over a few practice problems for physics. Again, we have a lot of these problems. So number one says, a uniform rod of mass m equals 1.2 kilograms and a length L equals 0.8 meters. Lying on a frictionless horizontal plane is free to pivot about a vertical axis through one end as shown. The moment of inertia of the rod about this axis is given by 1 over 3 ml squared. If a force F equals 5 newtons, theta equals 40, axis shown, what is the resulting angular acceleration about the pivot point? And then we have a pivot here with a length, and it pretty much shows us all of that. So first things first, if you've seen my last video, you know I like to write my knowns first. Okay, so we have all of our knowns and we want to know what angular acceleration is. So you can find acceleration through torque. And our formula for torque is right here. We have a lot of formulas for torque, but we need the one with the relationship between inertia and torque, which is going to be this one. And then we can also use the FL sine theta as well. So using these two formulas, we can now equal them to each other. The torque equals inertia alpha, and torque also equals FL sine theta. Since inertia is in this problem, this is inertia right here, we are able to use this equation. So now I'm setting them equal to each other, so putting 1 and 2 equal. So we have inertia alpha equals FL sine theta. Now looking at this problem, we can see the variable that we're trying to find, which is alpha, or angular acceleration, which you can see right here. So we're trying to find this, so we can almost isolate this problem to have alpha on one side, which is what we're looking for. So we can divide this side by the moment of inertia and isolate that angular acceleration that we're trying to find equals to FL sine theta. Now we can substitute I into here because we have I. This is I, moment of inertia, and this is inertia. So this equation is going to look like this. Divided by, and then if you divide this problem by 1/3, the fraction is going to flip. So the 3 goes on top, on the numerator, and you have ml squared. So now you can see we have an L in the numerator and an L in the denominator, so we can cancel this L, and then that makes a normal L, just one L. So now angular acceleration equals 3F sine theta over ml. And now we can plug everything in. So 3 times F, which is 5N, times sine theta, which in our case they gave us 40, all over mass, which is 1.2 kilograms, times length 0.8 meters. And now once you do all the math, your angular acceleration should equal 10.04 rads per second squared, because this is acceleration. Now, that's the answer to number 1. As you can see, right here, we got it right. Now, moving on to number 2, a horizontal force of magnitude 6.5 newtons is exerted tangentially on a Frisbee of mass 32 grams and a radius 14.3 centimeters. Assuming the Frisbee, a uniform disk, is originally at rest and the force is exerted for 0.08 seconds, determine the angular velocity of a rotation about the central axis when the Frisbee is released. So we're going to go ahead and write my notes. So I just wrote down our knowns, which is the force is 6.5 newtons, time is 0.08, radius is 14.3 centimeters, and we're trying to find angular velocity with the mass being 32 grams. Now, in SI units, we don't use grams, we use kilograms. So we're going to change this to kilograms, which is going to be the decimal point moved over 3 times. So 0.032 kilograms. Now, our radius is in centimeters, and SI units are not in centimeters. They are in meters, so we're going to convert this to meters as well, just going ahead and doing that. So 0.143 meters, because you move the decimal over to the left twice. Now we can get started with our problem. We are trying to find angular velocity of rotation. We can use this formula right here. So we can also use torque to find this velocity as well, because we are given a Frisbee, and a Frisbee is a disk, and torque does well with disk. Okay, we can use this formula for torque, and we can also use this formula for torque as well to help us find this problem. Torque equals R times F, cross F, which is radius times the force. And our second equation, torque equals inertia times acceleration. We can now set them equal to each other, where 1 equals 2, because they're both torque. R times F equals I inertia. And now we do not know what the angular acceleration is, so we can find that out first, because this is an unknown. So what we can do is use this formula right here, which is angular velocity equals angular velocity plus alpha t. Using this formula, we can now isolate alpha. So we have minusing this initial velocity to the other side. So minus this equals alpha t divided by t. And now alpha equals velocity minus velocity initial times over t. So we can use this equation and plug this in to this alpha to get this final velocity that we are looking for right here. So I times and then WF minus W initial over time. And now we know from this problem that the Frisbee is originally at rest. So there's not going to be an initial velocity. So this is going to be 0. Another unknown we can work on is the inertia. Now we do not know what the inertia is, but we know it's a disk or Frisbee, so we can use the inertia of a uniform disk right here, which is 1/2 meters times radius squared. We can plug this in to the I here. So we now have RF equals now 1/2 mr squared times WF over T. And now we're trying to find WF, so now we can isolate WF on one side to solve this equation. So we can divide this to bring this over here first. So when you divide a fraction, it kind of flips and multiplies. So it would be 2RF all over mr squared. And this R are the same. I don't know why I wrote it like that. They're the same. equals WF over T. And now we can cancel this R, cancel that, and multiply both sides by T because T is in the denominator. So now we have 2FT all over MR and then equals WF. So we have WF equals 2 times force, which is 6.5 newtons, times time, which is 0.08 seconds, all over mass, which is 32 grams, times the radius, which we, oh wait, not 32 grams, my bad, it was 0.032 kilograms. So, with the radius of 0.143 meters. And once you calculate everything, you should get 227.27, and this would be in radians per second. Moving on to the third problem, which says a 3 kilogram particle has a position vector given by r equals 2t squared I hat plus 3j hat, where r is in meters and t is in seconds. What is the angular momentum of the particle in kilograms times meters squared over seconds about the origin at t equals 2 seconds? So we have a lot of information, and we're going to go ahead and write it down. So I wrote down our knowns, which were the mass, the time, and the vector that they gave us. And now we want to find what angular momentum is, which is in this notation, L with the vector symbol over it. Now, there are formulas for this already, so we can actually use L equals M times R times V. It could either be these two, but in this case, we have a mass, so we want to use this problem, and we can get a velocity from our position vector. So velocity is actually the derivative of position, so that's how we're going to find our velocity for this problem. This is our angular momentum equation, and we're trying to find V now, where V equals the derivative of position. So the derivative of the position, which this is the position, is going to be 2, the exponent, times the constant. So 2 times 2 is 4, and now this exponent minus 1, which is going to be 1. So t to the 1, and it's going to be I hat. And since this 3 is a constant with no variables, this j hat is not a variable. It's going to be 0. So it's going to be 4 this plus 0. So we have 4t I hat for our velocity. Now we can plug this into our equation. So we have times, and now we can go ahead and plug in r as well. And now we're going to have to find the cross product between these two vectors. Now this is going to be in a vector, this is going to be ax, ay, and this is going to be bx. Where in a vector it's going to be I hat plus j hat plus k hat. So that's why we have ax plus yx, ay, and if there was a k hat, it would be az, because the I hat is for the x coordinate, j hat's for the y coordinate, and k hat is going to be for the z coordinate. So this position here is ax, this is ay, and this is going to be bx, where this is another vector b. So with this information, I'm going to give you the formula for the cross product, which we're just going to take a look at first because it's actually this really long one right here. This is how you find the cross product between the vectors A and B. So looking at what we have AX, AY, and BX. Well, the first point of I hat requires AY, BZ, and BY, and AZ. We clearly don't have any of the Z's, so we don't need that because Z is going to be 0, so therefore this just makes it 0. Second one, J hat also has an AZ, so this is going to be not included. Our third vector, K hat, is going to be AX, BY, AY, BX. Okay, so this is stuff that we have, this information we have. So finding this cross product, we can use AX, which is 2t squared times BY, which in this case we don't have a BY, so it's going to be 0 times BY 0, minus AY, which is 3, and BX, which is 4t. Okay, so this makes 0, so cross that out. So now we have m times negative 12t. And m is 3. So this is going to be equal to 3 times negative 12 times, and t, which in our case they gave us was 2 seconds. So we can already input that. And once you do all the math, you should get negative 72 kilograms times meter squared over seconds. And don't forget K hat. This is K hat. And that is the answer to the angular momentum for number 3. As you can see, we have negative 72 K hat. Okay, moving on to the fourth problem, which says, what is the angular momentum of a 0.21 kilogram ball rotating on the end of a thin string in a circle of radius 1.1 meters at an angular speed of 10.4 radius per second? So, going ahead and writing my notes. So I just wrote down all of our knowns, which was the mass, the radius, the angular velocity, and we're trying to find the angular momentum. So for this problem, we can use the inertia formula, which is known to be I equals the sum of mr squared. And as you can see, we have a mass and we have a radius. And we can also use, we need to actually use the angular momentum formula. But in this case, we are going to use the one for L equals IW. Because we have a W and we can always find our I because we have MR. So, L equals IW, which is momentum equals inertia times angular velocity. And now we have our inertia, which we can plug in, mr squared, and we know W is 10.4 radians per second. Now mass is going to be 0.21 kilograms times radius 1.1 meters times 10.4 rads per second. And oh, I forgot squared. That's really important outside of the radius. So once you do all the math, you should get 2.64 kilograms meters squared per second. And in this case, it's meter squared because it's angular momentum, and that is the unit of measurement for momentum when it's angular. Okay, number 5. A figure skater can increase her spin rotation rate from an initial rate of 1 rev every 2 seconds to a final rate of 3 rev per second. If her initial moment of inertia was 4.6 kilogram meter squared, what is her final moment of inertia? Our knowns are going to be our angular velocity final, which is 3 revolutions per second, with this, and they gave us revolution, the initial revolution with 1, and time equals 2 seconds. So this is actually the initial velocity, angular velocity, because it is 1 revolution per 2 seconds. So that's a speed right there. We are trying to find our final inertia. We have the initial, and we can actually use our angular momentum formula. Since we're trying to find the final moment of inertia, we can use our angular momentum formula. Now we can use this because it is a rotating rigid body, the angular momentum of a rotating rigid body formula. So we have, and in this case, we need to use the law of conservation of momentum, which says that angular momentum final equals angular momentum initial. So this means that IW equals IW initially, right? Using this law. So IW final equals IW initial. And since we need to find I final, we can isolate this side. So dividing both sides by angular velocity final. Okay, so now we have our formula to find the final momentum, and we can plug everything in. So I initial is 4.6 kilograms meters squared, with the angular velocity with 1 rev per 2 seconds, all over final, W final, which is 3 revs per second. And now we can do the math, and initial final, and inertia final should equal 0.77 kilograms meters squared. And as you can see, that's our answer right here.